For most of human history, solving a mathematical problem meant starting from scratch every single time. Scholars relied on a patchwork of trial and error and memorized shortcuts to find their answers. This lack of a unified system meant that every new scenario required a bespoke rule. Math wasn't cohesive. It was a collection of disconnected tricks that had to be memorized individually. As trade routes expanded across Asia, Africa, and Europe, these logistical limits became a liability for massive merchant caravans. Growing empires needed a way to calculate values faster and more reliably than manual guesswork. A solution emerged, treating the unknown as a tangible value. By using a symbol to represent a missing number, scholars created a single rule to solve every problem. Instead of asking for one specific answer, mathematicians shifted to logical steps that worked every time. Math was now a universal logical system. Scholars could finally scale their reasoning far beyond the limits of individual, isolated calculations. This new logic immediately changed daily life for merchants. By applying these systematic methods, business owners could calculate profits, exchange rates, and complex partnerships with a level of accuracy that was previously impossible. Systematic rules replaced the need for lengthy, manual transaction counts. This reliability saved time and protected businesses from the costly arithmetic errors that often plagued trade ledgers. The efficiency applied to the state level as well. Governments adopted algebraic procedures to manage massive logistical hurdles, allowing tax officials to estimate revenue for entire provinces with consistent accuracy. This mathematical precision extended into the legal system. Authorities used consistent formulas to divide land boundaries and calculate complex inheritances, ensuring that civil laws were applied with mathematical certainty. By replacing manual calculations with systematic rules, ancient institutions could finally expand their operations without collapsing under the weight of their own logistics. Engineers used these formulas to define the physical world before they even broke ground. By solving for unknown lengths and dimensions on paper, they could plan massive projects like this canal with extreme precision. Using these proportional relationships reduced structural errors. It allowed builders to anticipate the stresses on bridges and irrigation systems, making ambitious engineering projects more reliable and durable. Astronomers moved this logic from the Earth to the sky. They utilized algebraic formulas to track planetary motions and predict the exact timing of eclipses with a new level of mathematical rigor. These astronomical predictions directly improved navigational tools. Travelers could use the calculated position of the stars to find their way across oceans, effectively opening up the world to long-distance exploration. These calculated predictions gave builders and navigators proactive control over the physical world. This logic spread to Europe during the Middle Ages, as the works of Al-Khwarizmi were translated into Latin. Scholars who had struggled with older, more limited systems now had access to a universal mathematical language. European mathematicians aggressively adopted these methods, using them as the logical foundation for higher mathematics. They were no longer just counting, they were analyzing relationships. With a systematic way to solve for unknowns, scholars could finally move into higher-order problems. This logical infrastructure supported the scientific developments that emerged during the Renaissance. Students moved away from simply memorizing answers, focusing instead on the logical steps required to solve entirely new problems. This trained the mind for analytical reasoning, a method for understanding the world through logic. More than a millennium later, the modern era is still built upon this ancient logic of the unknown. We see it in our infrastructure. Modern engineers use algebraic principles to calculate the structural integrity and wind resistance of skyscrapers long before the first steel beam is placed. The same proportional calculations allow us to master aerodynamics. Every aircraft propeller and wing is a product of equations that solve for the unknown variables of lift and drag. This legacy lives in our technology. Computer programmers build the algorithms that power our world using the same algebraic logic that Al-Khwarizmi documented 1,200 years ago. Even our most advanced artificial intelligence and climate models are essentially massive algebraic systems. They solve for millions of unknowns by following the same logical steps used in the ancient world. Algebra remains one of humanity's greatest intellectual inventions, a universal language that continues to decode the universe and drive innovation in the modern age.